Hello, everyone. My name is Satvik Singh. I am currently doing a PhD under the supervision of Professor Nilanjana Datta at the University of Cambridge. And today I will be speaking about a recent project of ours titled Detecting Positive Quantum Capacities of Quantum Channels. Before I begin, let me quickly thank the organizers of QIP for giving me the opportunity to present my work here. All right, so let's begin. So as we all know, quantum channels model the most general physical transformations that can be applied to any given physical system, right? And the quantum capacity of a channel quantifies the maximum rate at which information can be sent reliably through the channel in the limit of asymptotically many uses of the channel. So essentially, it's just a number that is associated to any given channel, which is an embodiment of its information carrying capacity, right? So it turns out that to determine whether or not a given channel has positive quantum capacity is a very difficult open problem. And this talk is concerned with precisely this problem. And so in this talk, I will exhibit a simple yet powerful perturbative technique, which can be used to solve this problem for a wide variety of quantum channels. And so during the course of this talk, we will unravel an intimate connection between a channel's ability to transmit information and the relative sizes of its input, output, and environment spaces. So let's begin with some basic definitions. So a quantum channel is just a linear map between two matrix algebras, which is completely positive and trace preserving. Two quantum channels are said to be complementary to each other if they are related via an isometry. So this embeds the input space into the combined output environment space, and the action of the channel and its complement are retrieved by tracing over the environment and the output spaces respectively. So you first embed the input into this combined output environment space, and then you trace out the environment or the output. So essentially, the complementary channel, it models the information loss to the environment. And unsurprisingly, this will play a crucial role in determining the quantum capacity of the channel, as we will see now. So this is the famous LST theorem. So basically, the quantum capacity of a channel admits a regularized expression like this. So let's break this down. So at the base level, we have an entropic quantity called the coherent information of a state through a channel phi. This is nothing but the difference in entropy of the output and the entropy of the complementary output. And then when you maximize this expression over all possible input states, you get the coherent information of the channel. And finally, when you regularize this expression, you get the full capacity. So notice that Q1 of n copies of the channel is at least as large as n times Q1 of a single copy. Though this gives a trivial lower bound on the capacity, as the coherent information is the lower bound. And this inequality can be strict. And when this is the case, then we say that the Q1 or coherent information is superadditive. If equality holds here, we say that the coherent information is additive. And in this case, the capacity is equal to this Q1. And we say that the capacity admits a single letter formula because there is no regularization. And why is this Q so difficult to compute? So first of all, we have this optimization problem, which can be shown to be non-convex. And secondly, we have this nasty regularization term. So these two facts together makes the task of determining or computing capacity not very difficult. So currently only two classes of channels are known to have zero capacity. The first one is the class of anti-degradable channels. So these are the channels for which the output of the channel can be retrieved from the environment via some channel N. And for these channels, we can use some no cloning argument to show that the capacity is zero. Secondly, we have the class of PPT channels. So these are the channels which when acting upon one part of a bipartite state result in a PPT state. And for these channels, one can use the fact that no entanglement can be distilled from a PPT state to show that the capacity is zero. And then we have entanglement breaking channels, which lie strictly within the PPT and anti-degradable class. So they are defined in a way similar to the PPT channels, but now the output is not just PPT, but separable. So partial action of a channel on a bipartite state results in a separable state. So we have this picture, we have PPT channels, anti-degradable channels, and we have entanglement breaking channels inside. And we don't know whether there exists any other channels which are not in these classes, but still have zero capacity. And essentially the problem is there is no systematic way to determine if a given channel has positive capacity. And this is precisely the problem that we hope to tackle. And let me quickly mention that the first steps in order to solve this problem have already been taken by Vikesh in his recent paper. And I will mention the connections with his work, between his and our work in the later slides. So, okay, so the main idea, it begins with this lemma. So if you have a pure input state, then the output of the channel and the output of the complementary channel, they have the same non-zero eigenvalues. So this means that when you compute the coordinate information of a pure state with respect to a channel, you get 0, right? Because the entropy are equal. So this gives a trivial lower bound on the capacity, which just basically says that the capacity is non-negative, right? But now the idea is to perturb this pure state psi in such a way that you get a positive coordinate information, right? So we do this perturbation where the sigma is some arbitrary mixed state. We look at the outputs, which are also perturbed now. And then our aim or goal is to analyze this coordinate information function as a function of this perturbation parameter epsilon. And currently we only know that at epsilon equal to 0, we get the pure state, and so the coordinate information is 0. So in order to analyze this function, we use we borrow some techniques from perturbation theory. So this is a similar religious theorem. So this states that if we have two Hermitian matrices A0 and A1, and we perturb them like this, and let's say lambda naught is an eigenvalue of A0 with multiplicity n, then for sufficiently small epsilon, this perturbed matrix has exactly n eigenvalues that converge to lambda naught as epsilon goes to 0. And furthermore, these eigenvalues, they admit these convergent power series expansions. And furthermore, these first order correction terms can be computed from the non-zero eigenvalues of this conjugated matrix. So P0 is the projection onto the unperturbed eigenspace, and A1 is the perturbation. So the non-zero first order coefficients are precisely the non-zero eigenvalues of this matrix. So in our case, notice that we have these perturbed outputs, and we can immediately identify the A0, the unperturbed state, and the perturbation via this output of the mixed state sigma. Right. Okay. So the next steps is basically we will use this we will use this religious theorem to compute the eigenvalues of the perturbations, output perturbation and the complementary output perturbation. And once we have the eigenvalues, we can easily compute the coordinate information, which is a function of the eigenvalues, right? And once we have the coordinate information, we can show that its derivative will have the following form. So we'll have an unbounded term and then a bounded term. So notice that this term blows up as epsilon goes to 0, and the rest of the term will stay bounded. So this is crucial because, okay, so first of all, notice these k of psi and k psi c, they represent the orthogonal projections onto the unperturbed kernel. And this trace expression, the trace of k psi of sigma, this is the cumulative rate at which the 0 eigenvalue of the unperturbed output changes once you start the perturbation, right? And similarly, the other trace expression. So now notice that if this coefficient is positive, then as epsilon goes to 0, this first term will blow up, right? And so we will have a positive derivative for small enough epsilon, which will imply that the coordinate information itself is positive for small enough epsilon, because we know that at epsilon equal to 0, the coordinate information is 0, right? So this is the main result. We have a phi and we have a complement, its complement. And if there exists state psi and sigma such that this tracial inequality holds, then we can conclude that the coordinate information of the channel is positive. If the opposite inequality holds, then we can conclude that the coordinate information of the complement is positive. So this is the star theorem. Now, in order to study a very useful consequence of this theorem, we need to collect some crucial definitions. So observe that for any channel phi, it is easy to check that the support of phi acting on any state rho is always contained within the support of phi acting on the maximally mixed state or the identity. And this motivates us to define the minimal output dimension of the channel as just the rank of the output of the maximally mixed state under the channel. And similarly, we can define the minimal environment dimension to be the rank of, to be the same expression, but for the complement, right? So these are supposed to give the minimal size of the output space, which can accommodate all the outputs through the channel. And one can easily show that these numbers are basically related to the Choi rank of the channel. So the environment dimension is the Choi rank of the channel, and the output dimension is the Choi rank of the complementary channel. So whenever we are computing capacities, we can, without loss of generality, assume that our channels are minimally defined in the sense that these equalities hold. And why is that the case? Well, let's say that we have a minimally defined channel, phi, and we have an isometry which maps the output space to a bigger space. And let's say we define a new channel, phi twiddle, by isometrically extending our original channel. Then it's clear that because of this isometric relation, all the entropic expressions are going to be the same for phi and phi twiddle. And moreover, any complementary channel to phi can be shown to be complementary to phi twiddle as well. And that's why the capacities are not going to change. And this can be done for any given channel. So any given channel can be related to a minimally defined channel in this way. And that's why we can, without loss of generality, assume that our channels are minimally defined. Okay, so now let's recall the star theorem. We have this theorem, and now let's observe one more thing. So for any given channel phi, it is very easy to show that the rank of the output of any pure state through phi is going to be bounded by the minimum of the output, minimal output and minimal environment dimensions. So if we assume that this holds, then let's say we have a channel phi, which is minimally defined, and for which the output space is strictly smaller than the environment space. And furthermore, let's say that there exists a state psi which saturates this bound. So in this case, we'll have a state psi for which the output has rank d out, right? So now if we observe this trace expression on the left-hand side, the kernel is going to be 0 because the state is getting mapped to a full rank output space, right? Output state. But on the right-hand side, this kernel will be non-zero because we have seen that we assume that the environment is strictly larger than the output, right? And so in this tracial inequality, LHS is 0, but RHS is not 0 if we choose, let's say, sigma to be the maximum limit state. And so we can immediately conclude from the star theorem that the complementary channel has positive capacity. So we collect this result in this corollary, which was also independently derived by Vikesh in his paper. So we have two channels which are complementary to each other, and we assume that there exists a state psi that gets mapped to this maximal rank output state. If this is the case, and if the output dimension is bigger than environment dimension, then the channel has positive capacity. If the output dimension is smaller than environment dimension, then the complementary channel has positive capacity. So notice that in order to apply this corollary, two steps need to be performed. The first one is just to compute these dimensions and check that these are not equal to each other. So this is a simple step. But the second step is the hard one because we have to ensure that there exists a state which gets mapped to a maximal rank output state. So in general, this is very difficult, but in certain cases, when certain dimensional inequalities hold between the output, environment, and input spaces, the existence of this pure state, which gets mapped to a maximal rank output state, is automatically guaranteed. So in case that when these dimensional inequalities hold, we can immediately conclude that the channel or its complement has positive capacities depending on what inequalities hold. So basically the take-home message is that all these results are crucially dependent on the size of the output, environment, and input spaces, and that's a very important message that we need to take from here. All these results, especially these two inequalities that we have, these two results that we have here, they simply depend on the dimensions of the output, and so they can be very easily applied to any given channel. Now let's look at one other main result that we have. So we have seen that for any given phi, the rank of the output, it is difficult to check if there exists a pure state psi such that the rank of the output is this maximum value that it can take. But it turns out that for a randomly selected channel, this state is almost always guaranteed to exist. So let me clarify what I mean by randomly selected channel. So what we do is we fix an input dimension D and output dimension D out. And then we fix the environment dimension to be any integer which satisfies this inequality. And then we select an isometry randomly according to the Haar measure, which embeds this input space into the combined output environment space. Now we can define the channel via the usual Stein-Spring form, right? And then this phi is said to be distributed according to the Stein-Spring probability measure. And this probability measure is itself dependent on this environment dimension. So for every different environment dimension, we'll get a different measure. Now we can state our final result as follows. So for if we have a channel phi, which is distributed according to the Stein-Spring probability measure coming from this dnth environment dimension, and if d out turns out to be bigger than dnth, then we can be almost sure that the coherent information of the channel is positive. On the other hand, if d out is strictly smaller than dnth, then we can be sure that the coherent information of the complementary channel is strictly positive. So this is quite surprising, because what we've essentially shown is that whenever the output dimension of a channel is strictly larger than its environment, we can be almost sure that only a single copy of the channel suffices to detect a positive value of its capacity. And so this is in stark contrast with the general picture, where people have shown that there exist channels phi for which n copies of the channel for any given n can be 0. The coherent information of n copies of the channel can be 0, and yet the channel can have positive capacity. In contrast, what we have shown is that whenever the simple dimensional inequality holds, at just the n equal to 1 level, we can be almost sure that we detect the capacity. And this is independent of how the channel acts on the input state. This just depends on the size of the output and environment spaces, right? So finally, in the few minutes that I have, let me quickly go over some applications. So I will not go into much detail here. I will just quickly name the channels to which our results can be applied. So first, we have the depolarizing and transpose depolarizing channels. So these are important noise models in quantum information theory. And it was recently shown that in the qubit case, the complementary capacity of a depolarizing channel is strictly positive for all values of the parameter except 0. And what we do is we extend this result to arbitrary dimensions and to the transpose depolarizing family of channels as well. So this is the result. And notice that in particular, this includes the Werner-Holevo channel. So we can provide some non-trivial statements on the complementary capacity of the Werner-Holevo channel, which is a special case of the transpose depolarizing family. So when this parameter Q is d over d minus 1 on one of the extreme ends, then we get the Werner-Holevo channel, and we can show that this has positive complementary capacity whenever the d input dimension is bigger than or equal to 4. Then we have dephasing channels or Schur multipliers. So these channels take an input state and multiply it entry-wise by some matrix B. And so we can show that these channels have 0 capacity if and only if the channel itself is entanglement breaking. So we know one direction is clear. We have already seen that entanglement breaking channels have 0 capacity, but the other direction is a non-trivial one. So we show this equivalence. And then we can also apply our results to Pauli channels in arbitrary dimensions, and amplitude damping channels and multi-level amplitude damping channels as well in arbitrary dimensions. All right, so to conclude, we have seen that the problem of quantum capacity detection is quite challenging. And what we have done is we have developed a simple yet powerful perturbative technique, which can be used to solve this problem in a wide variety of circumstances. Our analysis reveals that the ability of a channel to transmit information is intimately connected to the size of its output environment and input spaces, the relative size of these spaces. And for instance, we have shown that whenever the output of the channel has larger dimension than its environment, then we can be almost sure that the channel has positive capacity. A single copy of the channel has positive capacity. And this result does not depend on the specific way that the channel acts on its input states. It just depends on the size of its output and environment spaces. And a couple of open problems. So recall our star theorem again. And the main issue with this theorem is that we don't know how to find the states psi and sigma for which these tracial inequalities hold. So that's a one hurdle that we need to overcome. And secondly, let's look at the random result. So we have seen that whenever the output space is larger than the environment space, a single copy of the channel has positive capacity almost surely. Now, what if we allow multiple copies of the channel to be used to detect the capacity of the channel. So when we do that, it is reasonable to expect that we get a stronger result, right? Maybe we can get rid of this probabilistic statement and prove that whenever the output is bigger than the environment, we deterministically have positive capacity and not just almost surely, right? So that would be a wonderful result to obtain, and we are currently working on whether that holds or not. All right, so with this, let me thank you all for your attention. If you have any questions, please feel free to contact us. Our email IDs can be found from one of these preprints, and these are some of the references that we use in this talk. Thank you.